Mute. There's still a catch in the story that I said, that when we use hybrid encryption, when we go to the bank, for example, we obtain the public key of the bank, and then we use it to sample one session key for encryption and one session key for authentication. And once we have the session keys, we encrypt everything, typically with AES, and we authenticate everything, typically with CBC AES, creating a MAC, or other mechanisms could use an HMAC with the second key here. However, how are we sure that the public key is the key of the bank? How many of us went to the bank, into the physical offices of the bank, scanned something with our smartphone or computer to make sure this is really the public key? I'm sure nobody did that. Which means we are vulnerable to what is called a man-in-the-middle attack. What if somebody inserts herself or himself on the path between the two, and we've seen ways to do that on a Wi-Fi public hotspot by forging ARP messages, for example, then we can get all the traffic and replay it. So this guy will sit in the middle between us and the bank, will receive the public key of the bank, and will send to us his public key, not the public key of the bank, but we'll pretend this is the public key of the bank. So we will do all that stuff. So we will share completely legitimate secret keys, but between us and this guy. And this guy will represent us for the bank. So we'll, of course, decrypt and obtain the validate the messages that we have sent, and we'll send them to the bank, but now with shared session keys that are created by the bad guy here. And whenever everything we send, in fact, can be transformed here, we can change the destination of a bank transfer here, and the bank will have the impression that everything is okay. So the problem was that the public key was not itself authenticated. So we need to verify the public key. So we've seen that in order to authenticate, we need public key. So the public key itself should be signed, right? So that's a chicken and egg problem. But like every chicken and egg problem, we start by first having a chicken or a hen that will lay the first egg. So this is solved by what is called digital certificates that use certification authority here. So a digital certificate is a piece of text that you must have. In fact, if you want to put a website online, and hopefully everybody today uses only secure transport to go to website. So you will need to do exactly what we do, even if we don't go to the bank. We will need to guarantee that our public key is the correct public key. To obtain this, you must have a digital certificate that you've paid probably from a certification authority, or if you put your website on Infomaniac or something like this, then you will need to, Infomaniac will do it for you. So the provider of the web hosting system will obtain the certificate for you from a certification authority. So it's a certification authority is a company that provides authentication to the world, Global Sign, for example, that will, the public key of whom is well known to Microsoft and Apple and whoever installs Linux. Here it's a bit more tricky, but if you get your software from a manufacturer, then the software will come with the public key of the certification authority. And then the certification authority will sign with their private key a piece of text that gives all the indication you want, which is a description that this is really a bank, the name of the bank, perhaps information like where is it registered, and will sign the public key of the bank here. So that when I will receive my this certificate, I can verify the certificate because the public key of the certification authority is known to me. So I can verify the signature here, and that authenticates for me the public key of the bank here. So this is how things are. So I will receive, in fact, when I go to the bank, as part of the setup of the communication channel using TLS, I will receive not just the public key of the bank, which would be, of course, too fragile because the attacker could send me something that they pretend is the public key of the bank. I'll receive the public key of the bank and a certificate that signs this public key with the signature of a certification authority. Right. Of course, the public key of the certification authority must be pre-installed in the device. If you install it manually, probably it doesn't work, because if you install a certificate manually, who knows whether this is not a certificate that has been given to you by the attacker, right? So simple. So in principle, you should never install a certificate. Sometimes we have to. EPFL, for example, forces us sometimes to install an EPFL certificate. And then we have to trust that we are on the EPFL network, that we are talking to a website of EPFL, and the certificate we're downloading is really this one. But this is a bit fragile. Some, as you see, some cases do it. The traditional way to do it is to rely on your browser. For example, Internet, Safari, or whatever you're using, that comes with the operating system. And if you use another browser like Opera or Firefox, and when you install the browser, you should validate the installation using the old browser that you use. That's why you should never download a web. Somebody says, oh, here's a fantastic web browser. Perhaps it's bogus because it has wrong certificates, for example. If you install a PMU, you have the same problem when you install hardware that has some software that will use encryption and authentication. It has also certificates, and it typically comes from the manufacturer. So when you buy a PMU from ABB or Siemens, you have to rely on them that the certificates are the correct ones. So there is always a bootstrap phase, which of course is fragile. And there is, might have heard the story of how the CIA attacked the Siemens company to install their own bogus certificates that allowed Americans to take control of some cyber physical systems in Iran, for example, because the certificates were corrupted at the company itself. So of course this can happen, but that's the only thing we can do today. Also, certificates have a validity time that's typically valid for a year, which also stresses that your computer, your device, your PMU should have a correct time. If your computer believes it is 20 years ago, it will accept a certificate that perhaps is not valid here. Browsers, if you use a recent browser, Edge or Explorer or Safari, or it will always check the validity of a certificate. In fact, if you use a recent browser like Chrome or Safari, and you go to a website that does not have a valid certificate, it will warn you and will, by default, it will refuse to go to this website. But you can use other browsers that will let you go to such websites, which is certainly a bad idea. And browsers typically display a padlock, a closed padlock here, that indicates that the certificate of this remote part could be verified. Old browsers a few years ago would simply display that the padlock was open and believe the users will pay enough attention to this. But the same browsers were polluting the screen with a lot of advertisements and the weather and the stock exchange. So of course, when there are so many graphical elements, you can't trust that the user will pay attention to all of them. As I said, modern browsers, or the very recent ones, will simply refuse to go to a website that is not correctly authenticated. Certificates are used for what is called secure transport. Last week, we saw the transport layer using TCP. But today, you don't use TCP without authentication and encryption in quasi all cases. Not always, but in fact, it should always be the case. So TCP, like UDP, provides no security and should be complemented. And the state of the art today, one of the two methods is TLS, the other is QUIC, that I will describe very shortly. And TLS provides everything that we've seen here. It provides encryption and authentication, uses hybrid authentication and validation of certificates. So it uses RSA to verify the signature that's on the certificates. It uses RSA to set up session keys, and it uses AES to provide encryption and MAC here. So this is what TLS does in a typical web browsing scenario. In a typical web browsing scenario, we authenticate only one end of the communication, the server. You go to the bank, you authenticate that this is really the bank that you're going to. The bank has not authenticated at this level of TLS, has not authenticated you, because your computer is not authenticated at the level of TLS by the bank. But once you have established a secure communication with the bank, typically there is a second phase where you need to authenticate to the bank by giving a password and typically giving a second authentication form using Google Authenticator or the equivalent of this that the bank does for themselves here. So the authentication is provided inside the connection. That does not authenticate the device, but that authenticates that the app that you're using has received the appropriate credentials from the bank here. So it uses, in an initial phase, a public key obtained from a certificate. We'll verify the certificate and use this, as we said before, to establish session keys here. And by having the certificate, if the certificate fails, that is probably because there was a man-in-the-middle attack, and the certificate is not coming from a bank here. And the two-way communication will use two different keys for encryption and authentication. The blue part is the sockets we've seen last week when we use TCP. It's a bit more complicated than UDP, but essentially is the same. We create a socket, we bind, and then we send or read from the socket. Typically, we should not just do that, but we should use what is called TLS sockets, which means that we should add to this, in addition, the formation of the security association. This is done typically by after creating a socket, adding something which is called wrap the socket on the client side, and on the server side, put the key and certificates, the private key, if that's the bank here, and the certificate that will be used by all the mechanisms we have seen. The net effect of that is when we do a connect, so the standard connect simply has the effect of doing a SYN, waiting for the SYN ACK to come, and when the SYN ACK comes, ACK the ACK, and only then we can send data. If we have used secure sockets, in addition, when that happens, there is a second exchange where we set up the security association. The security association needs to be set up because there are things like the nonces that we need to agree, what are the initial values of the nonces, and also what version of the protocols we are using. Because perhaps so far we had been using DES, and this is no longer what we use because we had a recent software update here, and we use AES, plus we're using SHA-2, and now we use SHA-3, etc. So the encryption software may change once in a while, not too frequently, but certainly several times per year. So we here agree on what are the encryption systems we use, and we set up all the initial values of the counters, and only when this is done, we can send here. So this is how TLS works. TLS is easier to understand when it works over TCP. It works also over UDP. Over UDP, we don't have this SYN, SYN, ACK phase, but we have the similar security association, which is very similar. TLS over UDP, which is called DTLS, is a bit more complicated because in TCP guarantees in-sequence delivery. So things like nonces and so on do not need to be re-advertised at every packet. In contrast, if we use UDP, or we can also do security without UDP directly on the IP layer, it's called IPsec, then every message, every datagram that we receive in the case of UDP is a standalone message, and you cannot assume that you have received all the previous messages, because with UDP, some of them can be lost. So the nonces, for example, need to be sent per message. So there are a few other details, but otherwise it's very similar. Voila, little quiz at this stage. In the slides, it's a bit further out, but let's do it now. Yes? I don't know if we have that slide. Well, it's a bit later. It's 68. Yeah. Close the poll in a few seconds. Closing. The correct answer, well, it depends on. Here, the public key seems to be sent outside of the CA, so A is perhaps true, perhaps not. It depends. In reality, it comes from the certificate, but this might be a bit misleading. B is obtained from the certificate, but certainly the validity of the public key is obtained by the certificate, but certainly not the public key of the certification authority. So the correct answer should probably considered to be D. It would defeat the purpose of certificates if you obtain the issuing public key of the certificate of certification authority from the certificate. Although this is sometimes done, it's called a self-signed certificate. Right? It's like when you were a child and you first day of school, you go to school and the school asks, give us a sample of the signature of your parents, and you give it. Then for the rest of the year, you can sign all the excuses because you have given the signature. So it would be the same here. Getting the certification authority public key from the certificate defeats the purpose of this. It must be out of band. It must be done from a source that you trust. And whom do you trust? Well, I trust this is a Windows computer. It was installed using Windows installation procedures. I trust that the browser that it had when I installed it, which was Explorer, had the correct certificates. And then I installed Chrome, and I believe that the installation of Chrome was verified using the certificates that were provided by Explorer. And now that I have the Chrome certificates, I believe that Chrome is correctly validating everything. So you can find the certificates depending on which computer you have. Those are files that are stored somewhere in your configuration. And sometimes you have to install manually some certificates. Those of you who do the advanced lab, you will have to install some certificates for parts of the lab. So, and in a smart grid or industrial context, we may have to install certificates, but of course this has to be done with extreme care. It should be done by knowledgeable people who install them on a disk or on a piece of storage that is taken with great care. Just don't take a USB key that is hanging around and could have been modified by anybody. So the certificates and the public key of the certification authority have, of course, to be taken very seriously. Now let's divert a bit from the security and return to some point we haven't seen last week, but is related to security. I said that the standard approach today is to use TLS. So when we use TCP, we should always use TLS on top of TCP. When we use UDP, we should always use DTLS. I say we should, in practice we don't always, but because there are legacy systems who don't do it, but it's unsecure. So we should avoid this as much as possible. In fact, there is now a replacement for all of this that is called QUIC, that has been initially developed by Google, but now has become a standard and is being deployed also by Facebook, by Apple, by other companies. It's no longer a Google company, Google stuff, which is a replacement for TCP and TLS altogether. What was the motivation? Well, the initial motivation, it's not clear exactly all the motivations are, but the one that is we can re-engineer today is to avoid this latency of setting up TLS. So when we, so taken from the viewpoint of Google, I mean, what is the major business of Google? It is Google search. You go to a web, so far, perhaps with ChatGPT and so on, things will change, but so far that is it. And what is Google search? Well, you go to a website and you receive one reply. And 99% of cases, you look only at the first page, right? So it's a one single message exchange. But in order to do this, you need to open a TLS connection, which means open a TCP connection, verify the certificates, all that stuff. And with TCP and TLS, so when you go to Google, of course, you go to the authenticated Google, even if you don't, it's not your bank, but still you want to make sure that what you get there is truly coming from Google. So you open a TCP connection, you open a TLS association, and that takes at least 2 round-trip times. Is it really a problem? It's not clear, but it's perceived to be a problem enough by Google so that they would like to remove that. So instead, what they do, they streamline everything and they do the reverse way. First, they establish the security association, and then they observe that when we doing the security association is considerably more complicated than doing what TCP handshake is doing. TCP SYN ACK is just exchanging a few sequence numbers and maximum packet size. You can put all this information also in the security association. So by doing this, you do it in one shot here. So that reduces the latency. But there's more fundamental than this. The idea is that you cannot use this alternative to TCP without security. You cannot open a TCP connection and do your business. You first have to establish a security association, and then you will get the TCP for free behind it. So making security mandatory is really I would say, also an important motivation. A third motivation that's important for us in the context of industrial networks is it allows what is called multiple streams. Remember that TCP is offers a streaming service. That means it sends all the packets one by one and guarantees to deliver them in order. And there's a single stream. Inside QUIC, you can have multiple streams, which will have benefits as we see here. Other than that, QUIC is the same as TCP. So it's not TCP, it is not using TCP, but since Google has hundreds of thousands of extremely highly qualified programmers who took networking courses, so they have the resources to redo everything. So they have redone TCP in QUIC by simply taking exactly all the same mechanisms of TCP. So everything we've seen, the windowing mechanism, the congestion control, we've seen that TCP does not only transport, but also takes care of managing the network and avoiding congestion collapses. So QUIC does it also the way, but with, as I said, one difference, which is parallel streams. And it runs on UDP, which seems weird. If you just see that for the first time, you say, in fact, there should be 3 transport protocols, UDP, TCP, and QUIC, which is true. That's how it should be. But for reasons that are practical today, it is quasi impossible today to invent a new protocol type because of the NATs. Remember all the NATs everywhere? How does your NAT work? It looks into the header for a TCP port number, if it has seen TCP as protocol type in the IP header, or a UDP port number if it has seen UDP. So if you deploy QUIC with yet another protocol type, you need to upgrade all the NATs in the world before QUIC will work. How long will it take to upgrade all the NATs? 20 years, probably. And it's not under the control of Google. So they decided not to invent which would be the clean way to do. They said there is a third protocol type for transport, UDP, TCP, and QUIC. Instead of that, they put everything in UDP. Remember, UDP is very basic. It does nothing else than add a port number. So that's what, and QUIC needs a port number, so it runs in UDP. But when we have UDP and QUIC, we have really something like TCP. We have reliable transport with acknowledgements and all the zoo of things. Except now that when we do a Wireshark, we will not see very much because everything will be encrypted, right? QUIC encrypts everything, so you don't even see the sequence numbers. They're encrypted. Also, QUIC has the benefit of removing what we have seen is the head of the line blocking. If we use TCP, which you do still today a lot, but if you use Google software and go to a Google website, for example, if you use Google Chrome to go to YouTube, you will use QUIC, presumably, and not TCP. But if you use Safari to go to YouTube, you will probably today use TCP over TLS. And as we have seen, TCP as a streaming service, that means on the receiving side, everything is put in a single buffer and delivered only as long as there is no loss here. There's no gap in the sequence. So here, if there are 3 objects in your web page, if, for example, a blue packet is lost, then the red object cannot be delivered if it happens that it was object sent as number 2 by the source here. Right. With QUIC, there is 1 receive buffer per stream. So as a QUIC program, as a programmer of QUIC sockets, you have to decide for each of the objects in which stream they go. And if a blue packet is lost, for example, that will not affect the transmission of the red here. So if you download a web page that has an image, a sound, a banner, if there is a part of the image that is corrupted, the rest of the web page will display correctly without waiting for the image. Whether it's a good idea to have images on the web page, that's arguable. I think not, but that's one of the motivations for QUIC versus TLS. So QUIC avoids the head of the line blocking if the applications use the many streams. For us in industrial networking context and in smart grid context, that can be interesting. Remember, we said last year that if we use TCP for a PMU to PDC application, this head of the line blocking might be counterproductive if the round trip time is not extremely small. The round trip time is microsecond and not, but if the round trip time is few milliseconds, since a PMU resends a new measurement every 20 milliseconds, if one is lost, the time it takes to detect it and resend it might delay the next measurement, which is stupid because the next measurement makes the previous one completely useless. If you have QUIC, then you can do 1 measurement, 1 stream per measurement. The streams in QUICs are as simple as simply putting a value in what is called the stream header in the QUIC packet header. So a typical PMU to PDC system that uses QUIC would use a number of streams, perhaps 10 streams, for example, and when a new measurement comes, it takes the next available stream and puts, for example, measurement M1 in a certain stream, and the next measurement M2 is put in a second stream. You don't need 1 million streams because after 10 measurements, for example, here, the time is very large compared to the round-trip times of the repetitions and loss detection. So for the measurement number 11, you might reuse stream 0 here. The effect is that if packet M1 is lost, for example, if measurement M1 is lost, it will be retransmitted by quick. But if M1 arrives before, this will not block at the receiver, which is the desired behavior. This is what we would like for the PDC side. We leave it to the PDC to decide whether M1 is useless or not. It depends on time alignment. Perhaps M1 is still useful because the PDC is waiting for measurements of this time period from others that have not received. Perhaps it's useless, and it's the PDC that will decide in this case. Instead of compared to using TCP, M2 is invisible here until M1, the loss of M1 has been repaired here. This has been implemented as a master thesis 5 years ago here, and that's the kind of things that we expect will come in the future of smart grids. So smart grids is a bit conservative in terms of networking, but I hope you will give a different twist to that in your professional life later. So smart grid already we had a hard time convincing smart grid people to use encryption and authentication at all. Now I think it's acquired, so they use it. The next step will be to use QUIC and the most modern encryption and solution. We have seen that TLS uses certificates, and certificates are used when we surf the web to authenticate the bank here. TLS can be used also for VPNs. Last week we've seen VPNs. If you have two parts of your private networks that are interconnected over the internet, we have seen that we can encapsulate all the packets from the right to go to the left as if we had a direct physical link from R to S, but we also need to protect them and to authenticate them. So one simple way is to use a TLS connection from R to S here. So every IP packet here will put as payload inside the TLS packet, which means will be encrypted, authenticated, and received by M here. This is a very simple way to understand VPN. It is not the most widespread one, although it is very frequently used. But other techniques that are used is, you can imagine, of course, a quick VPN. Instead of using TLS, you can use quick. The benefit would be that you can have multiple streams that can be used. For example, you can create one stream per source here, per source IP address. That will not delay, if a packet is lost here, that will not delay the entire tunnel, but will delay only one of the sources. So that is also coming, not very widespread because QUIC is new, but we expect this to be the popular solution in 5 to 10 years. And there are alternatives like DTLS. Instead of using a TLS over TCP, which is the simplest intellectually speaking, we often use TLS over UDP, or something that is called IPsec. IPsec is morally speaking, is the same as DTLS. It uses everything that TLS does, but on bare-bone IP packets. It encrypts, adds an encryption header, an encryption tailor. It authenticates using hybrid authentication like TLS does, but over IP packets directly, which is the normal thing we should do. But it's not very frequently used, not everywhere, and it's called IPsec. Apart from the existence of a UDP header, there's not much difference to that. There's a difference when we use Quick VPN or TLS VPN. There's a difference between those, which is that TCP does and Quick do congestion control. Congestion control means if there is here a packet that is lost, then the source that S, when S is sending to R, S will reduce the rate at which it's sending. Is this desirable? Is it not desirable? It depends. But in many cases, it is not desirable. It depends what happens. If you use PMUs that are streaming here at a constant rate, and you use the public internet, well, you should somehow be a good citizen in the public internet and avoid congestion. So since the PMU is not doing congestion control, it's a good idea that the tunnel does it. But if you do congestion control in your application here, it might be counterproductive to do it in the tunnel. Because if the tunnel becomes congested, it will reduce the rate. but it will be treated from a fairness viewpoint by this congested link that may be somewhere on the Swisscom network. It will be treated as one connection. Whereas it is past multiplexing, here I'm showing only one device, but in your intranet site, if you have 1,000 devices, you're multiplexing the traffic of 1,000 guys, and from a fairness, when there is congestion, from a fairness viewpoint, it's treated as one, which means, in fact, it will be treated unfairly. If there is a bottleneck here that's congested, the bandwidth of the bottleneck is divided between all the users of the bottleneck. The entire site will be treated as one, not 1,000 here, which means in practice, you may see poor performance of your TLS tunnel if you use it over a network that is susceptible of congestion. Those are the kind of side effects that we can see here. Let's conclude with a small case study on how we can combine everything we've seen to protect our network here. In a smart grid network, we typically do a distinction between the operational part of the network and the information part of the network. So there is the network that connects all devices together, for example, the PMU to the PDC. And there is the network that is used by people who work at Romand Energy to do their accounting and their job and send email and so on. So companies like an electrical utility has those two networks typically as separate entities, because of course, you want to secure much more severely the operational network. And also from a congestion and traffic viewpoint, they may be different. On the operational network, you will have a lot of devices on which you want to guarantee that they can work without congestion control. On the information network, then people browse the web, etc. That's a different thing. So typically, we put the PMU, PDC, SCADA. So PDC is the phasor data concentrator. That's the device that collects all the PMU measurements and put them together in what is called time alignment to then produce an estimation of the electrical state. You will see that in the coming week with Mario. The SCADA is the supervisory computer. If you've seen videos or if you've yourself visited the control room of an electrical utility, you'll see people sitting at computers with lots and lots of screens. Perhaps on the wall, there's huge screens that is showing what is happening. What is the state of all the lines? In a factory, it's showing what is the state of all the machines. And this is all controlled by this computer called the SCADA here. So this information typically goes to the PDC, and from the PDC or directly from the PMU also to the SCADA. So you have all this traffic here. How can we secure all this communication? Of course, if this is not secure, if this is over Ethernet cable, you might have some guy who comes at night, breaks the Ethernet cable, introduces a repeater in it, copies all the traffic, might forge the PMUs, and wait for a hostile country to launch an attack on the infrastructure, which might be in 5 years from now, and will destroy or make you lose control of this thing here. It can be also simply for countries that are at war, like Ukraine. This is what is happening today. For other countries like Switzerland, which is not at war, the problem is more simply ransomware. You might have attackers that attack your system and say, now you're under attack, you lose all control. If you want it back, pay 1 million in Bitcoins to us on this account. So most companies in Switzerland say that they have had such attacks already. Many attacks don't succeed, of course, but most companies are attacked. It's not something that happens by bad luck. It is something, just like if you leave your smartphone in the metro and you go away and you expect the following day to come into the same metro and find your smartphone, then chances are you won't find it here. So you don't do that, of course. You secure it. Well, it's the same for your operational network. If you don't do anything, you can be certain you will be attacked. If you do something, you will still be attacked, but hopefully the attack will not succeed. How could we secure everything? Well, here are 3 practical things that are being done today. The one certainly good solution is to encrypt everything end-to-end by using secure transport. This is shown by the blue lines here. So we use TLS over UDP if it's PMU, or over TCP, or over QUIC for other systems. And we encrypt everything end-to-end. Well, this will guarantee what? This will guarantee that an attacker that reads your traffic either here or all the Ethernet wires here will not be able to see the content of the messages and will not be able to tamper with them. The only thing they can do is possibly destroy them, but cannot modify the message and cannot read them, and will not be able to gain intelligence on what is happening in your grid. Right? As I mentioned, authenticating is, of course, the first thing you want to do to make sure an attacker doesn't forge the messages that your control system is using. But also the attacker will want to gain intelligence in order to attack a smart grid. You need to understand how the thing is run. It's not sufficient to be able to change a message. You also must understand how this is done. And the way this is, you understand it is by reading everything and then analyzing what happens. If you know a bit of this course, and if you read all the messages, you will understand which message is about sending a PMU measurement and which not here. So you will need to encrypt to prevent the attackers of gaining intelligence on what is happening. So that is certainly a good solution. Right. What is often done is to, in addition, protect the part that goes via the public network by using a VPN tunnel directly from the end device to a VPN server, if the end devices are isolated. If the end devices are in a substation, for example, you will do a VPN tunnel from a router in the substation to the VPN router here, that is called the VPN server here. So if you do this, you typically keep end-to-end transport, and now you have two layers of encryption. Here you have encrypted packets that are sent from the PMU to the VPN, to the PDC, for example, and the encrypted packet itself is encrypted in the tunnel here. What's the benefit of doing this? Well, people don't always feel comfortable sending things in the clear over a public network because this gives information on the structure of the network. You will see when we use this here, encryption takes care is at the best over UDP if it's, or over TCP if we use TLS, which means the UDP and TCP headers are sent in the clear. In particular, the source and destination IP address here. So I'm showing here one PMU, one PDC, but imagine you have 1,000 PMUs, which is more likely to be the case, and 5 PDCs here. You will know what are all the IP addresses of PDCs and PMUs, because you will see every 20 milliseconds a packet, right, which is very atypical. So by doing what is called traffic analysis, you will see the rate at which, so PMUs, a thing that sends a packet exactly every 20 milliseconds is a PMU. So we'll have the source IP address and the destination IP address of the PMU. So you will gain some intelligence on the IP addresses of the PMUs and PDCs here. So sometimes to avoid this, you will add a VPN connection. So you add more security to the initial solution. What I've seen being done, for example, the PMUs being deployed in the SIL of Lausanne, they don't do this because essentially they find it too complicated to use secure sockets. Or more probably because at the beginning when they did it, I'm sure, because I was part of the project, could not convince everybody to use secure socket from the beginning. So they used non-secured sockets like we did in some of the labs here. So the PMU software sends using regular sockets that are not TLS sockets, but a simple UDP socket to the PDC. Now comes SIL, and SIL says, well, it was fine as long as you were doing that at TPFL. Now that you do it on us, we want a security solution. Now, if you don't want to change all your software here, what you can do is to use VPN connections from every device to a VPN server and have what is called a secure area. So you put the PDC and the SCADA in a secured area, where an area where it will be, where you can assume that it will not be able to tamper with the Ethernet cable. Everything is locked and monitored. And the VPN server is the interface between the operational network and everything that goes over the public infrastructure, so that when a PMU sends packet, it sends them encrypted to the VPN server, and then the VPN server is the only place where the packet will be sent in the clear to PDC and SCADA. That provides a level of security that's very similar to the first one without having to deploy secure sockets. Hopefully in the future, secure sockets become something that we do naturally all the time, so that the second solution will be the one that is deployed. Voila, we come to the end of this lecture. I will conclude with the last quiz. How can we know whether we can type our EPFL on this website? I close in a few seconds. Closing. The majority says G all, which is probably the correct answer. We need to make sure the site is authenticated, which was true for this one. You see the padlock is closed, but what does it authenticate? Well, it authenticates that this is truly GitHub. It's not something that impersonates GitHub, it's truly GitHub, which means you should verify the identity. So the only verification of this gives, this is authenticated, but what is authenticated is the name that is here, so which is Peiju. Why should you give your EPFL passwords to Peiju? Well, there's no real reason. That's just an account I created on GitHub for exactly this attack here. So you should verify the site's URLs as expected. And of course, if you are taking risk and using a browser that you've downloaded on a Linux computer without checking whether the browser is a correct one, because somebody told you it's a very fancy one that blocks all ads and so on, perhaps all this authentication here is completely wrong here. So yeah, you need to verify all of this, which many of you did anyhow. Voila, that's the end of this part. That's the end of this security and communication part, which is a bit deviating from the main focus of the course. We will come back to it next week with Mario, and you will study with him state estimation. And after that, we will see how we use the control of the grid, combining all elements we've seen. Thank you very much.